Hello everyone, welcome to lesson 1.5. Today we're going to be talking about continuity, and like the last couple of times we'll be working through this video. You should be working through your packet at the same time. I may ask you to pause it to work on something, then restart the video, and there may be questions that pop up along the way that you need to answer on the Nearpod. Please make sure you work through all the Nearpod slides, read all of the details and announcements, just to make sure you're keeping up with things. It is your responsibility to go through the entire Nearpod, alright? Here we go. Today we're going to talk about continuity, defining it and how to use the definition of continuity to prove or determine whether or not a function is continuous at a point. All right. You probably have heard the word or continuity or continuous before. I want you to take a second, pause the video, and go ahead and write down for you what like an informal definition of continuous is. F of x is continuous at x equals c if, and then go ahead and fill in the rest of that sentence. What does it mean for something to be continuous? Pause the video and try that. All right. I hear lots of different things when I ask people to define the word continuous or continuity. Certain things I hear people say are that the function doesn't stop. The function doesn't stop or break. Sometimes I'll hear doesn't stop or break. I'll hear people say things like you can draw it. You can draw the function. Without picking up your pencil. And those are all good sort of layperson's terms for what something means to be continuous, right? But this is a math class, so we want to actually be able to pretty rigorously define what this thing means to be continuous, all right? If it's continuous, if a function f of x is continuous through x equals c, it needs to fit three qualifications, all right? And this is something you're going to need to memorize. You need to know these three criteria for continuity. Here's what needs to happen. If f is continuous at x equals c, that means f of c exists. In other words, we have a point there. The limit as x approaches c of f of x exists. And the limit as x approaches c of f of x has to equal whatever f of c is. So what does this mean? This means the following. If f of c exists, that means we actually have to have a point there. All right? You can't just put that to prove it. You actually have to write it out in mathematical notation. But what does it mean? It means that there's a point at x equals c. That makes sense. If it's continuous, we have to have a point there. This limit statement means that the limit at x equals c exists. We have to have a point. We have to have a limit. We have to have a point. There he is in space. We have to have a limit, which means the left side and the right side have to be coming together. And if it's going to be continuous, the left side and the right side have to come together at the same spot. And that's got to be where the point is. So that's what this last part takes care of. That the point that is defined, f of c, has to be equal to whatever the limit is. Because remember, a limit doesn't necessarily mean that there's a point there. But if the function is continuous at a point, it does mean that that point and the limit line up. In other words, this thing is just continuous. It keeps passing straight through that point. All right? Those are our three criteria. We'll be using those a lot. You need to file them away in your brain and never forget those things. 1, 2, 3 criteria. The stuff in black. Graphically, we can see this in kind of several different ways. Here's an example here. At c here, the function is not continuous. Notice that the function is defined. We have a point. The limit exists because from the left and the right, as x approaches c here, from the left and the right and the right do approach the same spot. But the function is not continuous because that limit, the place where the graph approaches, is actually not equal to where the point is. The limit and the point are not equal. So this function is not continuous at x equals c, x equals 2 here. We also fail to be continuous up here. There is no point. We'll call this, I guess that's at 3. The function fails to be continuous because f of 3 does not exist. So that would fail continuity right there. Over here, f of 5 exists. But notice that the limit from the left and the limit from the right are not equal. So that means that the limit as x approaches 5 of f of x does not exist. So in this case, f of 5 would fail continuity because the limit as x approaches 5 of fx does not exist, and we always use our proper notation. Same thing over here at 7. It's not continuous, but why? Well, f of 7 does not exist. Notice that the limit does not exist because the left-hand side and the right-hand side are not equal. So the limit as x approaches 7 of f of x does not exist. And if we want to talk about it, the limit does not equal the point, if we wanted to go ahead and add that in as well. So those are all points of discontinuity and why they are points of discontinuity. All right. Pause the video real quick. I want you to just, with your understanding right now, look at each of these graphs. I want you to label which of these graphs are continuous. If the graph is not continuous, identify which of the elements of continuity fails of those three. Does the point not exist? I want you to write it out as f of blank does not exist. Does the limit not exist? And say that the limit as x approaches blank of f of x does not exist. Or does the limit not equal the point? So pause the video and give that a shot. All right, let's take a look at graph number 1 here. It doesn't look continuous. We would need to pick up our pencil to draw this. But let's figure out why. Does the point exist? So yep, f of a exists. How about the limit as x approaches a? Well, from the left, the limit's down here. From the right, the limit is up there. So the limit does not exist, and that's what fails. So I can say, for number 1, not continuous because the limit as x approaches a of f of x does not exist. All right, let's take a look at graph number 2. This is also not continuous. Why? Well, look, there's no point here at f of a. So I can say not continuous because f of a does not exist. There is no value of the function here. It's just an asymptote, it looks like. 3. Is this continuous? No, looks like we have to pick up our pencil to get over that hole. So it's not continuous. Well, let's figure out why. We go down our checklist. Does f of a exist? No, f of a does not exist. So I can say this function is not continuous because f of a does not exist. There is no point there. How about number 4? Let's see. Does f of a exist? Yep. Does the limit exist? Yes, because the graph comes in from the left and the right around the same spot. Remember, I don't care that there's not actually a point there, but from the left and the right, the graph does approach the same thing at x equals a. But look, the limit that's down here does not actually equal where the point is. So it is not continuous. I could tell this because I'd have to pick up my pencil to be able to draw this little graph here with the hole and the dot. So this is not continuous because the limit as x approaches a, which is down here, of f of x does not equal f of a, where that point is, up here. And graph number 5. This graph is continuous. Notice to draw this, we wouldn't have to pick up our pencil to pass through where that point is. There's a point, the left and right side come together at that point, so the function is continuous. There we go. All right, I would like you now to do something kind of similar here. I want you to work through this graph and using the graph of the equation and the equation of f of x at the right. I guess let's scratch that. There is no equation. I'm not sure why I include that. Using the graph of f of x at the right. Identify the points of discontinuity. So list those out, x equals blank. And then using the definition of continuity, explain why the limit does not exist. Man, there's a bunch of typos here. Let's try this. Explain why the function is not continuous. I have no one else to blame. I write these things, so just my fault. Explain why the function is not continuous using the definition of continuity. All right, so let's try that again. Use the graph over here, the graph of f of x at the right, and identify the points of discontinuity. And then using the definition of continuity, explain why the function is not continuous at those spots. All right? Go ahead and pause the video, and there'll be a question that pops up afterwards for you to answer about this. All right, let's take a look. So it looks like points of discontinuity. We have points of discontinuity. I'm going to label them here, discontinuity. We have points of discontinuity at x equals -8. I see one right here. We got something funky going on. And what's going on there? Well, there, the limit as x approaches -8 of f of x does not equal f of -8. Notice the point and the function don't actually line up. Where else do we got discontinuity? We got one here at x equals -2. At x equals -2. What's going on there? Well, we have a point, but the left-hand side and the right-hand side are not coming together, so the limit does not exist. The limit as x approaches -2 of f of x does not exist. Right here, we have a point, but the left-hand side and the right-hand side are not coming together, so the limit does not exist. Do we have any other points of discontinuity? It looks like maybe over here. So at x equals 6. What's going on there? Where there is a point, but the left-hand side and the right-hand side are not coming together, so there's not going to be a limit. So I can say the limit as x approaches 6 of f of x does not exist. Also over here, the left-hand side and the right-hand side are not coming together at that x value of 6. Cool. So as we dive deeper into continuity, we'll notice certain things. The definition of continuity is really useful to explain why certain things are not continuous. But sometimes we can actually just base our understanding of continuity off of properties we are already aware of related to functions. First, let's try example 5. Explain how you know that f of x equals x plus 1 is continuous at x equals 3. Well, it seems a bit like overkill to go through the definition of continuity. I could plug in 3, f of 3 is 4. I could find the limit as x approaches 3 and find that. Actually, we need to write that out. F of 3 I know is 4. The limit as x approaches 3 of f of x is 4. I know that because I can just substitute in like we practiced, right? And we can say then that the limit as x approaches 3 of f of x equals f of 3, which is 4. Therefore, f of x is continuous at x equals 3. But that's kind of like overkill. We can just rely for some things on our knowledge of functions. This is a linear function, right? So we could have also simply said, we know f of x is going to be continuous because it is a linear function. Linear functions are always continuous. Let's take a look at example 6 here. Explain how you know g of x equals this thing is continuous at x equals e. So we know it's continuous at x equals e. So let's check our 3 continuity things. First, we need to check off what is, oh, not f. This is a function we're calling g. Let's do a different color too to kind of mix things up. Let's do this kind of blue color. All right. Let's check our continuity. 1, does g of e exist? So we come over here. When x is e, which branch do I plug it into? The top one, because the top takes x is greater than or equal to e. So I would need natural log of e. If I want to evaluate g of e, natural log of e is saying e to what power gives me e? The answer is 1. Let's check the second part. We need to make sure that the limit as x approaches e of g of x exists. Now this is a little funky. E, notice here, is our breaking point. So if the limit's going to exist, the left-hand branch and the right-hand branch actually have to be equal to each other. So let's check that. If this overall limit's going to exist, that means the natural log of e has to be equal to 2 e minus, to the e minus e. Notice I'm taking the left-hand side and the right-hand side and setting them equal to each other, because if they're going to be equal to each other, then the overall limit will exist, because this is really checking the left-hand and the right-hand limits. So let's see. Natural log of e, we already said was 1. 2 to the e minus e, that's 2 to the 0. 2 to the 0 is 1. Look at this. The limit does exist. All right. So I can come back over here. The limit is 1. And then our final statement here, the limit as x approaches e of g of x equals g of e, which was 1. Therefore, g of x is continuous at x equals e. So to explain how we know it's continuous, we have to check there's a point there, find the right branch to plug it into, make sure the limit exists, make sure the 2 branches are coming together at the same spot, therefore the limit exists, and that the point equals the limit, write it out in the proper notation, and make your conclusion. All right. Let's do this. I want you to, in a second, pause the video and determine for each of these functions if the function is continuous at the marked value. So pay close attention to the marked value, so 3 here, or 1, or at 0. If it's not continuous there, explain how you know using the definition of continuity. All right, write out using proper mathematical notation. Go ahead and pause the video and give that a shot for A through H. All right, let's go ahead and rock and roll about this, okay? We want to explain why these functions are continuous or not at their point. All right, x equals 3, it doesn't look continuous. It looks like the reason this guy fails is that the limit as x approaches 3, we'll just call it f of x, does not exist, right? There is a point at x equals 3, but the left-hand side and the right-hand side are not coming together. All right. How about over here? Well, it doesn't look continuous. We got a hole, and that would mean that f of 1 does not exist. That would be why it fails. We could say not continuous. We could say over here, not continuous. All right, how about C here? We want x equals 0. Well, it looks like the left and the right-hand side are coming together. So we have a limit there. We have a point. But look, the point does not equal the limit. So I can say the limit as x approaches 0 of f of x does not equal f of 0. Would be why it would fail. This is not continuous. Over here at x equals 4, this guy looks okay. It's got a, we could draw that section without picking up our pencil. So this guy over here is continuous. Nice. All right. How about here at x equals 2? That's supposed to represent a vertical asymptote there. Well, do we have a point there if that's a vertical asymptote? No. So f of 2 does not exist. And then this is going to be not continuous. All right, at -1, ooh, we got like a big gap over here. This is definitely not continuous. And why is it not continuous? Well, we could say it's not continuous because several reasons. It looks like we don't even have a point there maybe, but definitely we have a gap in terms of the limit. So we could choose either one of those. We could say that the limit as x approaches -1 of f of x does not exist. It'd be enough to prove that. At -2 over here, it looks like we got a section that we could draw without picking up our pencil. So this is going to be continuous there. And then over here, we got a funky situation. We got a point coming in here, and it jumps way on up there. That's supposed to be an asymptote there, and then it swings back down. So we do have a point, but the limit from the left and the right are not equal, so the limit overall does not exist. The limit as x approaches -1 of f of x does not exist, which means that this guy over here is not continuous. Cool. And there we go. All right. So a couple thoughts around continuity. When given functions in algebraic form, we can actually make some conclusions, kind of like I mentioned before with the whole linear function thing. We know that all polynomials, exponentials, sine, cosine, radicals of the form that have an odd root, that they are all going to be continuous. They're always going to be smooth, continuous things. There's going to be no discontinuities, no holes or gaps or anything. For rational-looking things, for fractions, they are going to be discontinuous wherever the denominator is 0, right? Since we can't divide by 0, right? Now, radicals that have even roots, so the even root of f of x, or y equals the log of something, are going to be discontinuous wherever f of x is less than 0. We know we can't take like the square root of -4 and have a real number. Similarly, we can't take the log of -10 and have a real number. All right. So we can say, since in this case we're going to call them the arguments, the things that are inside those functions, the arguments must be greater than or equal to 0 for roots and greater than 0. Oh, I'm not sure why I did it that way. And greater than 0 for logarithms. All right. So there's some basic sort of rules about continuity related things, okay? To help speed up your processing. Let's take a look at some actual functions now. Let's identify any points of discontinuity that we can, and then identify why these are points of discontinuity using the definition of discontinuity, okay? Some examples here. Let's see. F of x, it's a rational thing, so it's going to have a discontinuity when the denominator is 0. So I can say we have a discontinuity at x equals 3. All right. We can do some investigating about why here. Let's see. Let's just out of curiosity, that's the numerator factor. Let's see, x minus 3, x plus 1. That factors then, right? That's correct. Okay. Over x minus 3. So we definitely have a discontinuity when x is 3 because we can't divide by 0. But what do we have? We have a whole is what it looks like. So it's discontinuous. This function is discontinuous because if it's a whole, all it means is that the point doesn't exist. So we can say because f of 3 does not exist. Right, that's a whole. This graph is going to look something like that. All right. How about b here? Let's see. We got a cube, difference of cubes thing here. This is a good reminder. Do you remember your difference of cubes factoring? Let's give it a shot. The difference of cubes factor looks like this. Same sign, so we give a negative. Then we have the opposite sign, so it's a plus. And then always positive over here. So there's our factor for the difference of cubes of x cubed minus 8. If you actually FOIL this out, you would find, in fact, that you would get back over here to our original x cubed minus 8 expression there. All right. So what do we do with this? Where is this thing going to be discontinuous? Well, if you remember your difference of cubes, this thing over here is always going to be positive. There's nothing we can actually do to make this negative or 0 even. It's always going to be positive. So we don't have to worry about this, but there's definitely a discontinuity at x equals 2. And it looks like it's a whole again because we see x minus 2 up top. We can say because f of 2 does not exist. All right, C over here. When dealing with piecewise functions, we really only need to care about where we're going to see breakpoints. If we're going to check continuity, we really don't care about these transition points, these breakpoints that might happen between the different branches of the piecewise function. It looks like our only interesting spot here is x equals 2. Something's going to happen when x is greater than 2, when x is 2, and when x is less than 2. So let's see. We can even use our little continuity checklist. Does H in this case, I guess, does H of 2 exist? Well, H of 2, if I plug in x equals 2, there's the rule, it would be 4. So H of 2 does exist. Okay, that's fine. How about the limit? We can check the limit as x approaches 2 of h of x. So if we're going to check the limit, we need to check the left and the right-hand side. We don't care what happens at x equals 2, just the left and the right-hand side. So let's see if those things are going to be equal to each other. If we have the left-hand side, set it equal to the right-hand side, when x equals 2. So that make the left-hand side here, 3 times 2 is 6, plus 2 is 8, equals, let's see, if I square that, that'd be 8 plus 12. Oh, sorry, 8 plus 12, that's weird. And it's not even 8. Back up, Markwalter. 4 plus 6 is 10 minus 2 equals 8. All right. So the limit does exist. We can say that the limit as x approaches 2 of h of x equals 8. But there's the problem, right? Our limit, which is 8, does not actually equal our point. So our final statement over here, I'll kind of move it this direction, sorry y'all, is that the limit as x approaches 2 of h of x does not equal h of 2, right? The limit was 8, we found by checking the left and the right-hand branch, but the actual point was at 4. It would be a situation where we have a limit that exists, but the actual point is below it. Therefore, h of x is discontinuous at x equals 2. All right. I'm going to change color here so that we don't get super confused. Let's take a look at this other piecewise graph here. All right, we can check each of those things also. 1, does our point, it looks like maybe we'd have a problem here at -1. That's sort of our breaking point here. And oh my gosh, look at this. 1 over x plus 1. We're definitely going to have a problem possibly at x equals -1 here. So I plug in p of -1. Well, when x is -1, I look in the top branch. That will be 3 to the -1. So that's 3 to the first power. So 3 minus 1, which is 2. I can check my limits. So I check my left and my right-hand branches. I'll make them come together. 1 over x plus 1. Is it going to be equal to 3 to the negative x minus 1? At that trouble spot, that spot where it might be breaking. So at x equals -1. If I plug that in, oh my gosh, I end up with a vertical asymptote. This thing does not exist at all. So look at this. This limit is definitely not going to exist, right? This limit is not going to exist. I can't even put an equal sign here. Right, this limit over here is not going to exist because when x is -1, we have a vertical asymptote. So I can say we have a discontinuity at x equals -1 because the limit as x approaches -1 of p of x does not exist. All right, there we go. Now, when we're talking about discontinuities, there's actually 3 main types of discontinuity. A point at which a graph is not connected, but can be made connected by filling in a single point, is called a whole or removable discontinuity. I'm going to abbreviate discontinuity. We also call them holes. What does it mean, not connected but could be made connected by filling a single point? It means we have a graph that's chugging along. It has a single point gap and then keeps on going. And then we can make it continuous simply by plugging that hole there. So we call them removable discontinuities because it's like we removed a single spot. A place where the graph increases or decreases infinitely, we think of those sometimes as vertical asymptotes, have another name. They're called infinite discontinuities. Infinite discontinuities. And a place where a graph stops, moves to a different point, and leaves a gap is called a jump discontinuity. A jump discontinuity happens in piecewise graphs where this guy's coming along, maybe it stops right there and then jumps up to a new spot and keeps on going. That'd be a jump discontinuity. All right. These happen a lot in piecewise functions, and actually that leads us to this special note here that in piecewise functions, we really only need to check piecewise functions for continuity at the transition or breaking points there between the different branches at the transition points, because you might end up with situations where between the branches we get a big gap, but the branches might also line up nice and evenly, and we end up with having a continuous function. All right. We're getting close to wrap it up here. So now that we have this idea of different types of discontinuities, let's say we want to identify where f of x is not continuous algebraically. We can skip confirming with a graph for today for these. Identify why it's not continuous there, and then redefine it as a piecewise function so that it is continuous for all x values. So let's take a look at f of x. F of x. First, we want to identify where it is not continuous. So I can already tell the denominator is going to give us problems, right? The denominator is going to give us problems, so I know this thing is going to be discontinuous at x equals -1. But let me go ahead and factor out the top because we've found that that is actually kind of a useful tool. X minus 4 x plus 1 over x plus 1. And this function is going to be discontinuous when x equals -1. All right, we did the first step there. Now we got to identify why it is not continuous there. Well, it looks like f of x is discontinuous at x equals -1. We got a hole there. So because f of -1 does not exist, we can go a step farther and say it is a removable discontinuity. And the fact that it is a removable discontinuity, f of x does not exist when x is negative 1, but it is removable, is really important. We've now identified where the function is not continuous, why it is not continuous. Now let's redefine this so that it would be continuous. If all we have is a removable discontinuity, a hole, we should be able to plug that hole. We just got to figure out where we need to plug that hole. If this is some graph that just has a hole, the limit does exist. So let's actually find its limit. The limit as x approaches that problem spot, which is negative 1, of x minus 4 times x plus 1 over x plus 1. The whole cancel out, leaving us with the limit as x approaches negative 1 of x minus 4, which will give us negative 5. So we just found out the limit of this graph, where it comes together, is negative 5. But there's a hole there, right? If we want to make this function continuous, we need to put a point where that limit is. So we need to put our point at x equals negative 5. So we can redefine this piecewise function like this. This piecewise function is going to follow our initial function, x squared minus 3x minus 4 over x plus 1 when x does not equal negative 1. But when x is negative 1, we go, well, what's going to fill that hole? What's going to make this function continuous? Well, if we did have a point there, we would want the point to be at negative 5, because then the point would match where the limit is. And if the limit equals the point, then our function is continuous. So look at this. We've now redefined the original function as a piecewise function so that it is continuous. To do that, we had to find what the actual limit was at that discontinuity and then use it to redefine that point that plugs the hole. All right, I want you to pause the video here and do number 2, all right? It has a sum of cubes in it that you might need to look up, but I want you to try number 2 using those same steps. All right, so let's take a look at it. We can already tell that this function is going to be discontinuous at x equals negative 3 because, well, yeah, g of negative 3 is not going to be defined, right? Because we'll have a 0 in the denominator then. So we can say because g of negative 3 does not exist. That'd probably be the quickest way to do that. But if we want to try to, so we've already identified where the function is not continuous and why it is not continuous. Again, like I said, we're not worrying about confirming with a graph right now. We've identified where it's discontinuous, why it's discontinuous. Let's see if we can redefine it so that it is continuous. So this sum of cubes will factor. We keep the same sign, opposite sign, and then always positive. Let me do a quick double check, make sure that came out all right. All right, all over x plus 3, and we can tell right away, look at that. Oh, let's actually back that up. When we go to do our limit then, the limit of g of x as x approaches that problem spot, if we cancel out where our hole is really just going to be the same thing as the limit as x approaches negative 3 of x squared minus 3x plus 9. And when I substitute in negative 3, I get 9 plus 9 plus 9, so 27. All right, so there's where my limit is for my g of x function at my point of discontinuity, and I can use that to redefine g of x. G of x then is going to be x cubed plus 27 over x plus 3, because that function is all good as long as x is not negative 3. But when x is negative 3, that hole, if I want to plug it, it needs to have a value of 27. Alrighty. Let's identify whether this function h of x has any points of discontinuity, and if so, describe what fails and how to redefine it to make it continuous. All right, looks like our only awkward place in this piecewise function is going to be happening here at x equals 2, right? At x equals 2. Hold on one second. Wait a minute. We want to skip this one. I already used this one. I thought so. Man, I got a couple typos in here, got to fix. We already essentially did this one, right? We already did all the work for this. We did that up here, right? And we found that the limit was at 8, but the point was at 4. So actually, if we want to go ahead and fix this then, remember earlier we found that the limit, if we used the two branches, came together. The limit did come together at a value of 8, but that h of 2, the point was defined at 4. So if we actually want to redefine this, all we would have to do is scrap where the point is and say, all right, let's make the point 8, because then the limit on both sides as x approaches 2 will go to 8. And if that is the case, and the point is 8, then the function will be continuous. Now, one of the skills you'll see come up that's used to test this a lot is making a function continuous by defining some variable in the function that ensures that the function is continuous. Here's where we go back to the definition of continuity to make this happen. What do we need to check? Let's see what the problem is. Determine values of a and b that will make the function h of x continuous for all values. All right. So if we want to make this function continuous for all values, let's take a look. It looks like we got two different kinds of breaking spots in this function. We got one at -1. So let's start with that one. If h of x is going to be continuous at -1, we have to have a point. So let's see, when x is -1, do we have a point? Yeah, we sure do. If we plug in -1, I get -1 squared plus 1, so that'll be 2. So we'll have a point. Then we need to make sure that the limit exists. So the left-hand branch, which is up here, and the right-hand branch need to come together. So let's actually check that. Really what we're going to do here is we're going to check the limit. We know the point exists. We want to check the limit as x approaches -1 of h of x. And we're going to do that by checking the two branches. We know the point exists over here, so let's check the limit. All right, so we want to check that. So 5 minus ax has to be equal to x squared plus 1 when x equals -1. So if I plug in -1, I get 5 plus a equals 2. Oh, cool, we actually solved this because that's what we want. I determine the values of a. So what does a need to be? A would need to be -3 in order to make this limit to exist, right? A would need to be -3. And if the limit exists, and a is -3, look, it turns out that the limit would be 2. And when we plug in -1, we found that the point was 2, so everything will now be continuous, and look at that. We have now found the value of a that will make this function continuous. We also got to do the same thing for b. So does the point exist? If I plug in 3, I go to the middle branch here. That'd be 9 plus 1. So yeah, 10. The point would exist. For the limit to exist, I need to make sure these two branches are going to be equal. So let's do that. Are the two branches across x equals 3 going to be equal? Well, that'd be x squared plus 1. Is it going to be equal to b plus 4x at x equals 3? Well, let me plug in 3. 3 squared, that'll be 10 plus b, sorry, not plus, equals. We want it to be equal to b plus 12 if this is going to be, if the limit is going to exist, right? In this case, we are checking the limit as x approaches 3 of h of x. We check our two branches, left and right branch. We're doing that. We plugged in 3. Now we're solving for b. -2 equals b. So look, if b is -2, the limit will exist, and the limit will be 10, which is where the point was. So look, this function is now continuous at x equals 3, and look, we have found a and b. All right. I want you to pause the video now and go ahead and answer exercise 6 using the same kinds of skills. Find the value of a that will make this function continuous. Pause the video and then answer the question that you'll see pop up. All right, as a quick recap, to check continuity, we need to check the point exists, so f of 1, but f of 1 we know exists because we can plug in 1 down here, and that'll give us 7. We need to check to make sure that the limit exists, the limit as x approaches 1. That's going to be our trouble spot, right, of f of x. And that's usually where our work is for these kind of piecewise function things like this. So if the limit exists, that means ax squared minus 2 has to equal 3x plus 4 when x equals 1, that breaking spot there. So when x is 1, that would have a minus 2 equals when x is 1 there, that'd be 7. That's where the point is. So in order for the limit to exist, that means a would need to be 9. Because if a is 9, the limit exists into 7 and matches up with the point. So a has to be 9, and we're finished. All right. So what I'd like you to do now is there's a series of multiple choice questions here I want you to try that review all kinds of limit related things that we have done so far. Some of them are meant to be a little challenging. Give them all a shot, and then they go down to this next page. And then answer the questions that pop up on this Nearpod video. So pause the video now, do the multiple choice problems, and answer the questions that pop up on the Nearpod video, please. All right. So I'm actually not going to review these. I want to collect your data on this to see how you all did on this, and then maybe make some changes based off of how people are doing, all right? Cool. To do a quick recap, I want you to brainstorm right now. Don't look back in your notes. Brainstorm, that's not the right word. Recall. Don't look back in your notes. What are the 3 criteria for continuity, and write them down. Pause the video, please, and write down the 3 criteria for continuity. All right, here's the reminder, the things we need to take away. 1, we need to make sure f of c exists if something's continuous. 2, we need to make sure that the limit as x approaches c of f of x exists. And 3, we need to make sure that the limit as x approaches c of f of x is going to be equal to f of c. And if all 3 of those things are true, then the function's continuous at x equals c. As a fun little exercise, you can give yourself problems like this to do as well. Construct a piecewise function whose limit exists at all x values in its domain except at x equals 3. That can be fun. You can maybe make something like f of x equals, I don't know, we could do something as simple as 2x plus 1 as long as x is less than 3. And then we can say e to the x as long as x is greater than 3. Oh, greater than 3. And notice that this piecewise function is continuous for all, has a limit for all values, except at x equals 3, right? Because when x equals 3, I plug in at the top here, and I'd have 6 plus 1 is 7, but e to the 3 is not going to be 7, so the limit does not exist at x equals 3. All right. That's continuity for today. Please make sure you answer the exit ticket. And take a look at the optional homework problems. Remember, I highly encourage you to do the optional homework problems. It is the best way to make sure you're actually ready for everything you need for the test and for like the Unit 1 test, but also the AP exam and your college courses beyond. Please finish filling out and completing the Nearpod, and I'll see you next time. Bye.